me the possibility to present studies on the mode of action of transition metal-based drugs. I'm Iogan Tolbatov. I'm currently a postdoc at the Institute of Chemical Research of Catalonia in Spain, and my co-author is Professor Marrone from the University of Chieti in Italy. Metallodrugs are currently an essential part of a tool set of a medicinal chemist due to a variety of its features. So metallodrugs may obtain a wide range of coordination geometries and numbers. They can attain various redox states, and it is possible to synthesize novel derivative complexes on the basis of existing metal scaffolds via modification of ligands. The history of bioinorganic chemistry has started with the discovery of anti-cancer properties of cisplatin, the first registered metallodrug. However, cisplatin also produces heavy toxic effects, specifically nephro and neurotoxicity, and that is why novel transition metal-based metallodrugs are constantly being developed. They are developed via two possible routes, either via modulation of their carrier and labile ligands, it is the ligands that stay with the metal center and the ligands that are detached from the metal center during the activation process in the biological milieu. And also assembling active ligands and metal scaffolds, developing dual-acting drugs. Today I will show to you also an example of dual-acting drugs. You will see what I mean. All the studies that I'm going to present today are based on the usage of density functional theory. When doing these studies, we always try to select the best effective core potential for description of relativistic effects of the transition metals. We try to use the biggest possible basis set, and we use the long-range corrected density functionals for a better description of the geometry and electronic energy. Firstly, I would like to tell you about our study of arsenoplatin, a platinum-based anti-tumor metallodrug. Its mode of action can be well seen at this scheme 3. So it firstly approaches its target, that is denoted by X at this scheme. Its target is usually a protein residue. Afterwards, the protein residue takes the place of chloride, whereas chloride is cleaved. And in such a way, the adduct of arsenoplatin and the DNA or protein, its biomolecular target, is formed. And after some time, the platinum-arsenic bond is broken, and arsenic is released, and arsenic is cytotoxic. So we studied the interaction of arsenoplatin with various protein residues, histidine, methionine, cysteine, selenocysteine. We studied both thermodynamics and kinetics. That's why we also found the transition states for the reactions with considered nucleophiles. And here are the reaction profiles. We have found that the reactions with deprotonated cysteine and selenocysteine are largely exergonic. So their barriers are quite low, 15 kilocalories per mole, which suggests that the time of the reaction is less than 10 minutes in biological milieu. Whereas the reactions with histidines are slightly exergonic, you can see -1 kilocalorie per mole, whereas all other studied nucleophiles their reactions are not favorable with arsenoplatin. We compared our results with experimental data, so with the X-ray structures of adducts of arsenoplatin with model proteins. And indeed, these experimental data corroborate well results. We find here the adducts of arsenoplatin with histidine and with cysteine. The primary conclusion of this study was that deprotonated cysteine, selenocysteine, and histidine are the targets of arsenoplatin. Arsenoplatin reaches its targets in its naive unactivated form because the reaction-free energy for the hydration or for the equation of arsenoplatin is too high, so arsenoplatin is not activated by water before it reaches its targets. And the platinum-arsenic bond is not significantly affected when replacing chloride. So we suggest that the release of the arsenic moiety is subsequent to protein methylation and may be kinetically influenced by the protein environment surrounding the platinum 2 binding site. Another drug that we have studied is AS101. It is a tellurium-based compound. Recently, tellurium-based drugs have drawn interest because of their promising therapeutic properties. AS101 is used currently for treating psoriasis, genital warts, dermatitis, various cancers, and HIV. It is the first tellurium-based agent reaching human experimentation. Here is its form. You can see there is a glycol, and there are 3 chlorides. Our experimental collaborators from the universities of Pisa and Florence in Italy have developed the bromide and iodide analogs of this complex, and we made a joint experimental computational study for the activity of these metal scaffolds. The reaction mechanism which we studied was the mechanism for the activation of the drug in biological milieu. So there is an attack by 2 water molecules which detach the glycol fragment from tellurium center. And this tellurium oxygen with 3 halide piece, it is the true pharmacophore, as was noted by our experimental collaborators. We have calculated the reaction profiles, and the main thing that we noticed here is that the metal scaffolds with bromides and iodides are less stable than AS101, so the scaffold with chloride. So our conclusions are the following. Such a small modification, so we changed chloride to bromide or iodide, change the activation profile substantially and may have various biological effects. These studies that I have presented to you may provide useful indications for the design of novel tellurium-based drugs, and we found that the derivative complexes of AS101 with different halides are less stable than the original drug. However, they react more easily. The third study I would like to describe to you was the study of auranofin and its derivative. So auranopin's structure is here. It is the only gold-based metallodrug that has reached the human experimentation. Initially, it was designed as an anti-cancer drug. However, currently it is being repurposed to treat the superbugs, so the bacterial infections which cannot be treated by conventional antibiotics. So it was found that it is efficacious against gram-positive strains and not efficacious against gram-negative bacteria. However, the knowledge on how it works on a biomolecular level is largely missing. That's why computational study is important here. The only thing that was known previously was that it targets the thiol and selenol containing proteins. This is its structure. So the thioglucose fragment here on the left is detached, and the true pharmacophore is here, and it attacks its biomolecular targets. Our collaborators from the University of Pisa have developed the derivative structure with adding acetylcysteine to gold instead of thioglucose. So they studied the minimum inhibitory concentration values for these both structures for Staphylococcus aureus and Staphylococcus epidermidis. And they found that the derivative with acetylcysteine shows an abrupt activity drop against Staphylococcus epidermidis. So why does it happen? We have found that the gold-sulfur bonds in auranofin acetylcysteine is slightly more stable in comparison with auranofin. It happens because the bond has a great electrostatic character in case of auranofin acetylcysteine, and that we got from our study of the molecular charges on these complexes. Calculations showed that the activation profiles for auranofin and its derivative are similar, yielding comparable amounts of released active species. Thus, the lower lipophilicity that of auranofin acetylcysteine, rather than the slight difference in gold-sulfur bond enthalpies, may better account for the diverse antimicrobic activity of this auranofin analog. So it is active on Staphylococcus aureus and less active on Staphylococcus epidermidis, as it was found by our experimental collaborators. And the last part of our study that I would like to present to you is the study dedicated to the rhodium and the ruthenium-based paddle wheel complexes. These paddle wheel complexes have such exotic structure. There are always two metal centers, which are bridged by four ligands arranged around them in a lantern-like fashion. These ligands all contain carboxylates. So both rhodium and ruthenium-based paddle wheel complexes are efficacious against various cancers. They both have various toxic side effects. However, it is well known that the targets of the dirhodium-based paddle wheel complex are the DNA in its double and single-stranded forms, proteins, peptides, whereas the ruthenium-based complex is less well studied. The bridged ligands may be just acetates. However, scholars also add here various pharmaceutical agents, such as non-steroidal anti-inflammatory drugs and various other drugs, which make out of this paddle wheel complex a complex of double action, dual acting drug. The hypothesis on how it works is the following. Firstly, it attacks the protein residue and becomes attached to it while losing its axial ligand L, you can see. After some time, the metal-metal bond is deteriorating, and two monomeric metal complexes, monometallic complexes, are formed, whereas part of the bridging complexes are released. And if these complexes are the pharmaceutical agents, then we get the double action here. So, and here I would like to show to you our first theoretical result. We have found that indeed the addition, for example, of a nucleophile, for example, a deprotonated selenocysteine, in the axial position of this paddle wheel complex, indeed it increases the distance between two metals, which indeed suggests that the metal-metal bond becomes weaker. In case of rhodium, this difference is not that high. However, in case of ruthenium complex, indeed the addition of nucleophile at the axial position weakens the metal-metal bond significantly. We studied the dirhodium and diruthenium-based paddle wheel complexes. We studied the substitution reactions in which the axial ligand was lost and the nucleophile X was took the place of the axial ligand. We studied various protein residues, and for all of them, we of course used the simplified models because to save the computational cost. So we studied two protonation states for cysteine, selenocysteine, aspartic acid, and C-terminal. Whereas for histidine, lysine, arginine, and N-terminal, we looked only at the neutral protonation state. So we studied both the kinetics and thermodynamics for these reactions. That's why we also found the transition states for the dirhodium-based scaffold and diruthenium-based scaffolds. We got the results for the thermodynamics. So the majority of these reactions are exergonic. So the most exergonic reactions are with arginine, cysteine, histidine, lysine, and selenocysteine. For these most favorable reactions, we studied the kinetics, finding the transition states. So these are our conclusions. Complexes based on rhodium and ruthenium display similar preferences. They react more favorably with deprotonated cysteine and selenocysteine. Aspartic aspartate, deprotonated C-terminal, and histidine are the primary targets due to the bulk exposure. And in case when there is a higher pH of the biological milieu, then the water in axial position of the diruthenium complex becomes deprotonated, a hydroxo is formed. In such a case, a chloride exchange becomes favorable, and this exchange is very, very nicely selective. So we recommended to our experimental counterparts, we recommend this pathway to synthesize novel drugs based on these scaffolds. So substitution of acetates with sterically hindered groups or ligands bearing ionizable groups might be employed to enhance targeting of surface over core protein residues due to steric effects, acidity of the aqua ligands by favoring the formation of more selective metal complexes, and the downstream release of ligands that are pharmaceutical agents becomes facilitated. So what is the summary of this mini review that I presented to you? First of all, it is important to adopt the smaller models for the biomolecular systems. In the studies on arsenoplatin and pedal wheel complexes, I have shown to you that we have used the simplified models for the protein residues in order to save the computational time, whereas the accuracy was corroborated by the experimental data. It is important to understand mechanistically how the activation of these complexes happens in the biological milieu, as it was shown in the study of activation of AS101 and its derivatives. The analysis of the metal-ligand coordination allows to understand better the differences between similar metal scaffolds with various ligands, as I have shown to you in a study of auranofin and its acetylcysteine derivative. Inclusion of bulky ligands allows to fine-tune the metal scaffolds, as it was shown in the study on pedal wheel complexes. So the biological milieu, its effect is crucial onto the reactivity of a metallo drug after its administration into physiological conditions. And finally, my final conclusion here is that DFT computations permit to accurately characterize the behavior of a metallo drug in physiological conditions. Three main parts. So its activation, the activation of metallo drug, which is essential before the biomolecular target is reached. The undertaken ligand exchange scheme, yielding its binding to a biomolecular target, and the ability of metallo drugs to attack multiple targets. I would like to acknowledge the help and supervision from Professor Marrone, University of Chieti in Italy, my collaborator, and also the supervision of my bosses, my current boss, Professor Maceras from ICCSA in Spain, and my former supervisors, Professors Re, Coletti, and Florale Sar from University of Chieti Pescara and University of Burgundy in France. And thank you very much for your interest in our research.
Thank you. Thank you for your presentation. Any question? No? Thank you again.
Thank you very much.
Thank you. So let's proceed with the next presentation. And the title is Formulation for the Split Delivery Capacitated Profitable Tour Problem.
Okay, hello. I
Hello.
hope you can hear me all
Yeah.
and see the screen. Okay, is
Yes.
this working?
Yeah.
Okay, good. Then hello everyone. My name is Marvin Kasper. I'm a first-year PhD student of the University of Kaiserslautern-Landau in Germany, and I would like to present our paper about formulations for the split delivery capacitated profitable tour problem. So I would like to start with a short motivation where we talk about vehicle routing problems, where the objective is to find optimal tours for a fleet of vehicles to serve a set of customer locations. Here we see in this visualization, the red points and the blue points are customers, And in the middle of the picture, we have a depot depicted with a 0. And then the task is to find optimal tours through the different points under the objective to minimize the transportation costs, which are based on the traveled distance. And to mention here is that in the vehicle routing problem, every customer location is served by exactly one vehicle. In regard to practice, such customer locations can return different prices, also called rewards. And regarding a given available capacity, because of the finite space in the vehicle, not all customer locations might be visited. And those request acceptance decisions must be made in such problems, which is called vehicle routing problems with profits. So this is a superclass, and this superclass contains 3 different problems, which I just want to shortly discuss. The first one is the price collecting tour problem. There we have a lower bound on the cumulative price that must be collected. The second problem is the orienteering problem, where we have an upper bound on the costs. So there the tour has a specific length that must be met. And the third problem in this superclass is the profitable tour problem, which I will discuss in this paper. And in this profitable tour problem, we must decide which requests to accept and in which order to process them. So here's the objective to maximize the profit. The cumulative price net of the costs becomes the objective function. So on the one side, we want to get a high cumulative price in regard to accepting such locations. And on the other side, we also want to have low transportation costs. And to mention here, the assumption that a demand may be fulfilled by more than one vehicle is known as split delivery in literature. And this split delivery can make logistics more efficient and therefore also more sustainable. And in regard to practice, such split delivery applications can be found in many practical applications. Here I just want to mention 2 examples. The first one is the waste management, where, for example, the quantity at different points can exceed the capacity of a vehicle, because trash vehicle can not be so large to collect all the waste on one location, and thus we need several stops at this collection point. So it's logically that we need more than one vehicle to pick up all the trash. So this is such a case where we need split delivery. Another case, for example, where this split delivery takes place is routing of helicopters for crew exchanges. So so typically more than one helicopter is needed to bring crew members to a collection point. So not all people of a crew can be brought to the place with one helicopter. So we need typically more than one helicopter. And so this is another example where split delivery is needed. So now I would come to my problem definition. As I already mentioned, it's the split delivery capacitated profitable tour problem. So here we need to determine the most profitable tours for a given fleet of vehicles to serve a set of accepted requests locations. So we see that we first need to find the locations which we will accept under the conditions that we need to respect the vehicle capacities, and we completely need to satisfy the request demands, which are given at the specific request location. And thus the objective function maximizes the difference between the price we collect because of the accepted request location and the transportation costs. So, and in solving such a problem, in general also for all the vehicle routing problems, there we need to talk about subtours. So subtours are sequences of locations that are visited by a vehicle in a certain order before the vehicle returns to the depot. And these subtours must be excluded. And there are many different ways to exclude such subtours. We will discuss this in the following. Here in this picture, I depicted such a subtour. So we see the vehicle here would drive from 0 to 1 and from 1 to 0, and at the same time from 2 to 3 and from 3 to 2. And this is obviously a subtour. So we need to forbid such cases. A feasible tour would be if we would drive from 0 to 1 and from 1 to 3, from 3 to 2, and from 2 back to the depot. This would be a feasible tour, and such subtours must be excluded. So first of all, such a short remark for the variables and parameters and sets. So V is the set of all requests n and the depot 0. And we also have a binary decision variable here with 3 indices. And this binary variable equals 1 if an arc ij, also an arc ij is the connection between two such points out of V, and this equals 1 if this arc is part of the tour of a vehicle K, and otherwise else. Otherwise it's 0. And there's also a binary variable zi that equals 1 if the request I is accepted and 0 else. And we also have a variable to quantify the quantity that is delivered. It's an integer decision variable, qik, that indicates that the quantity delivered to a request by vehicle K that specifies the delivered quantity. So here a short illustration of an optimal solution of our problem. Here on the left hand side, we have an optimal solution with split delivery, and on the right hand side without split delivery. So as I mentioned before, the depot is labeled with 0, and all the other points are potential requests with their location. So here the first number is always the price we will get if we accept this request, and the second number is the demand that is demanded from this location. And here, as I said, on the left hand side, we allow split delivery. So we see this location is served by 2 vehicles. So the first vehicle drives this tour and goes also here to this location, and the second goes on this way also to this location and then back. And here on the right hand side, we see that there is no split delivery, and all request locations are only served by 1 vehicle. And here, if we do some calculations, we will see that on the right hand side, we collect a price of 26, so 5 plus 5 plus 3 plus 8 plus 5. And we have transportation costs of 4 plus 1 plus 1 plus 4 plus 4 plus 4 plus 3, so 21. And then we see that we have in total an objective value of 26 minus 21, and this is 5. And here, if we do this calculation, we will come to 33. That is the price we collect because of serving the different request locations, minus 27, the transportation costs. So we get here a total of 6. So we see here without split delivery, we only get an objective value of 5. And allowing split delivery in this case, we get an objective value of 6. So we can see that split delivery makes this better for the company, and there's a higher profit in the end. So now I want to shortly discuss our different problem formulations. We propose 3 different mixed integer linear problem formulations for our problem. The first one is a flow formulation with directed edges. So here the variables are asymmetric. So in this case, x0, 1, k equals 1, but this means that x0, x1, 0, k does not need to be 1. And here the subtool-elimination constraints are based on DFJ. That's Danzig-Ferguson-Johnson subtool-elimination constraint, which was published in 1954. And we will soon see how this works. In the second problem formulation, we also use the same subtool-elimination constraint, but here we regard undirected edges. So here the decision variables are symmetric, which makes the problem more easy. So now here we see how this works. Just short visualization. So here the example from before, and we want to forbid that this subtour takes place. So we want to eliminate this. How does this works? So if we regard this subtour elimination constraint from the DFJ, we see that we have to find the subtours for all request locations, which where the subtours have at least 2 elements. So I just wrote the 4 possibilities here. And if we write the constraints down, we get 4 different constraints. And here in this constraint, we already see that x23k plus x32k must be lower equals 1. And so we already see that this is forbidden. So here we can eliminate such subtours with these kind of constraints. And now we want to go further and think about how is there another way to eliminate such subtours? Yes, there is. Another important subtour elimination constraint was given by Beanstalk in 1993. And here we define a sigma set where, again, all subsets are regarded and all these decision variables summed up over this sigma set must be greater equals 2 multiplied with such a binary decision variable which equals 1 if the request at this location is visited by the vehicle. So how does this works? Here again, I wrote down all subsets for this short example. And here we see that this subtour will be eliminated by this. Then imagine that 2, 3 equals 1. Then we see that here the binary decision variable h3k must also equals 1. And this left-hand side must be greater equals 2 then. So either x03 or x13 must equals 1. So if x13 equals 1, then we already see with this that with this one we see that h1 equals 1 and a connection to the depot is then made, because if h1 equals 1, one of these trees must be 1. So there's a connection to the depot made. And on otherwise, if x03 equals 1 directly, we see that there's a direct connection to the depot. So we can also eliminate such subtours on this way. And I see I'm a bit short in time, so I will continue with the experiments. So just to say, we used 2 different test instances from the literature where we tested our split delivery in the capacitated profitable tour problem. And these instances were already used by Archetti in 2009. Archetti is a professor in Brescia, North Italy. And these test instances were also used for the well-known vehicle routing problem already in 1979. So there are many papers who have already used these instances, and we benchmarked them with the optimal solutions from Archetti from 2009. And we also gave each solving case 1 hour of computation time. And here, just to mention, we had between 50 and 199 different requests. So with also different request location and a fleet size between 2 and 4 in the first case of our experiments, and a vehicle capacity of 50, 75, and 100. So here, just to say, we see here the first instances. They are also the smallest instances. And here we see at the beginning, all 3 formulations solve the problem optimal. So here are always the computation times. But if we see the instances get larger, then we see that the first problem formulation could not solve them optimal anymore, while the second and the third perform better here. And if we summarize experiments for instances with under 100 request locations, we get an average value of these, where we see that our third problem formulation gets the best objective value. And we also see that in general, averaged over all instances up to now, we get an improvement of 2.4% because of allowing split delivery. And we also see that in general, there is also a mid gap. So the solutions are not optimal yet, but we can say even without leading to an optimal solution, split delivery improves the average solution within these instances by 2.4%. And if we conclude this for all these instances, we see that our first formulation has the worst performance overall, and the second and the third either find optimal solutions faster or yield a lower mid gap than the first formulation. And we can also compare the second and the third formulation for these instances. And there we see that the second formulation is only better in 12 out of 90 cases than the third formulation. So to sum up, we can say that the beanstalk subtotal elimination constraint perform better in these cases than the DFJ formulation. So then just shortly, our second part of the experiments, we extended the instances in size, which were also tested by Archetti in 2009. And here we see that this is the final important value, where we see that split delivery drastically can increase objective value in such instances when there's a high ratio of demand to vehicle capacity. So compared to the first part of the experiments, here in the second part, the demands are relatively much larger. And there we can conclude that split delivery has some big positive effect in this case. So in regard to time, yeah, I think it fits. I can come to a conclusion. We have seen that split delivery can significantly improve our current solution. As I said before, 13.5% was possible in these instances, which was already used in 2009 by Archetti. And there's a significant difference in performance when using the different MIP formulations. We have seen that the first one leads to very poor results, and the second and third leads to much better. And there we can conclude that the third tends to perform better than the second. So for future research, we can say that besides this exact procedure for solving our problem, we can also use some heuristic methods where we should investigate if we can reach good solutions in a sufficient amount of time. And we can also regard scenarios where the demand can even exceed vehicle capacity, as I already said in the beginning with the waste management. And we can also imagine scenarios where requests are not deterministic anymore, where parameters are uncertain. Yeah, thank you for your attention.
Thank you, Marvin, for your presentation. Any question? No question? Okay, thank you again, Marvin.
Yeah, thank you.
The next presentation is multidimensional scattered data in varying scattered data meshless interpolation for sensor networks. But I don't see the author. I will skip this presentation for now. And the next is Fast Buddha, Geomagnetic Map Builder.
Yes, hello. Do you hear me?
Yeah.
Okay, I will immediately share my screen.
Okay. Go full screen, please.
Yes. Okay, is it good now?
Yeah.
Oh, okay, thank you very much. Hello, dear audience. My name is Delia Spridon, and I'm PhD in physics and also a PhD student in computer science at the Transylvania University of Brașov, Romania. I'm presenting now our work entitled Fast CUDA Geomagnetic Map Builder. To do a short resume of my presentation, it contains a short introduction of what our work is about, few words about the importance of geomagnetic data. Then I'll talk about GPU programming, especially CUDA architecture, spatial interpolation methods insisting on IDW and kriging techniques, and also their GPU implementation. Also, the results we obtain and conclusion and the perspective regarding our work. In the end, a few selective references. So in this research, we use two interpolation methods, IDW and kriging, to generate geomagnetic maps in Romania. The algorithms for these methods are parallelized using CUDA architecture on GPUs in order to obtain fast, high-resolution magnetic maps for the studied area. The accuracy of the obtained maps are compared for the two interpolation methods. Also, the algorithms are analyzed, taking into account the execution time and the speed up. So geomagnetic data, as you probably well known, is information gathered about the Earth magnetic field and can be collected using a range of methods, including magnetic surveys conducted from aircraft, ships, or ground-based instruments. Geomagnetic maps are graphical representation of this data that shows variation in the strength and direction of the magnetic field at different locations on the Earth's surface. Geomagnetic data and maps are used in a wide range of scientific, industrial, and commercial applications, from understanding the Earth's structure to identifying the potential mineral and energy resources. As examples, geomagnetic maps are used in navigation systems such as compasses and the magnetic sensor to determine the orientation of objects relative to the Earth's magnetic field. This is particularly useful in situations where other forms of navigation, such as GPS, are unavailable or unreliable, such as in underground tunnels or underwater. Another example, geomagnetic maps aid in studying and monitoring environmental phenomena. Changes in Earth magnetic field can be indicative of natural hazards such as earthquakes, volcanic activity, or geomagnetic storms caused by solar activity. Monitoring this variation helps in understanding and predicting these events, uh, providing valuable information for disaster management and early warning system. Also, geomagnetic maps are essential for studying space weather and its impact on satellite systems. They help in predicting and mitigating the effects of geomagnetic storms on satellite communication, GPS accuracy, and other space based technology. By understanding the Earth magnetic field, scientists can better predict and manage the impact of solar activity on space based systems. So, why, as I told you, already told you, our algorithms were parallelized using GPU programming. So, a short uh, resume of what GPU programming is, also what CUDA is. Um Initially, graphics on PC were performed on such called VGA controller. In around 97, VGA controllers were beginning to incorporate some three-dimensional accelerating functions, including hardware for triangle setup and rasterization and texture mapping and shading. Hardware was able to these triangles into individual pixel blend colors and apply decals of pattern to pixels. In 1999, uh, NVIDIA developed such called GPUs. Original GPUs were purely fixed function devices, meaning that they were designed to specifically process stages of graphics pipeline, such as vertex and pixel shaders, but they have evolved into increasingly flexible programmable processors. Modern GPUs are fully programmable, many core chips built around an array of parallel processors. So um, in 2007, NVIDIA developed also this CUDA, and just after 2 years, I found this review that shows the progress was what progress was made until then. So in just 2 years, um, this CUDA was used for a wide range of application in various domains, starting with the financial domain to astrophysics or molecular dynamics. It can be seen that impressive speed up had been recorded for all study domains, starting with 17 in isotropic turbulence simulation and up to 100 speed up in astrophysics or in financial simulation, 100, almost 150. So, what is this compute unified device architecture? This is a parallel computing platform and application programming interface model created by NVIDIA. CUDA allows developers to harness the power of NVIDIA graphics processing units for general purpose computing tasks. CUDA enables developers to write programs that can be executed on GPU, taking advantage of its massive parallelism and computational power. With CUDA, developers can write code in programming languages such as C, C++, and Fortran, using an extension of these languages called CUDA C, C++. CUDA enables developers to write programs and models, taking advantage of this massive parallelism that could be applied. Taking into account the aim of this work, just few words about interpolation methods. Methods used to obtain geomagnetic maps. So the interpolation methods are used to estimate values at location where measurements are not available. There are several interpolation methods that have been used for this purpose, each with its own strengths and weakness. Some of the interpolation methods for geomagnetic data are IDW, Kriging spline interpolation, radial basis function, or newly artificial neural networks. Overall, the choice of interpolation method depends on the characteristic of the data and the specific research question being addressed. The interpolation method for geomagnetic data continues to evolve with new methods and approaches being developed and tested. IDW method, so inverse distance weight method, is a special interpolation method used to estimate values at unmeasured locations based on the values observed at nearby location. It assumes that values closer to a target location have more influence on the estimated value than those far away. IDW is widely used in geographic information systems, environmental sciences, and various other fields where special data analysis and interpolation are required. The IDW methods calculate the estimated value VU at the target location XY with the coordinates XY by assigning weight to the measured values VI at nearby locations based on their distances from the target location. So VU is given by this formula, and the weight is calculated by the below formula, where L is the distance from each sample location to the estimated location, and P is a positive exponent that controls the rate at which the weights decrease with distance, and K is a total number of sample location. If P is 2, then the method is named inverse square distance weighting, or if it's 3, it's inverse cube distance weighting. One of the main limitations is that this method assumes that the values being estimated are a function of the distance only, and it does not take into account other factors that may influence the values, such as topography, soil type, land use, elevation. Another limitation is that it produced unrealistic estimates at location far from sample locations, especially when the sample locations are unevenly distributed. Despite its limitation, IDW is widely used in various fields, including geology, environmental science, and geography. It is often used as a baseline method for comparison with other interpolation algorithms, and it is also used for simple application where high accuracy is not required. Here is the algorithm we used for this method, where G, I, J are the points of the to the grid of M or N interpolated values. M and N are natural numbers higher than 0 for a rectangular region given by the coordinates x min, x max, y min, y max. Kriging is also a special interpolation algorithm that estimates unknown values at unobserved location based on special correlation among observed values. The basic idea behind kriging is to estimate the unknown value ZU at an unsampled location U based on a weighted average of the observed values x z of x or I at nearby sampled locations xi. The weights are chosen to minimize the prediction error and are determined based on the spatial correlation structure of the data. The kriging weights are obtained by solving a linear equation that express the spatial autocovariance function data. I don't know how to. Okay, I'll skip and I'll go to results because it's time. Still, I have here the algorithms we implemented to calculate the kriging predicted values. So we need first to calculate the semi-variance point, and using those we calculate the semi-variance coefficients using least square method to obtain the weights WK weights kriging weights that will be used further to calculate the predicted value for each grid point. For the parallel implementation, we need to first to parallelize the algorithms. In the IDW, we parallelized the distance calculations between unsampled points. Also, the distance calculation between unsampled point and sampled points. And also we parallelized the calculation of weights for each sampled point. In kriging, each algorithm that I showed you was parallelized, assigning for each thread one calculus. The studied region was, as mentioned, Romanian, so it's a Romanian region. Here it's the images obtained by IDW in left, and in right it's kriging method map, and it can be seen some differences between the two methods, but the main difference can be seen here in the results by studying the errors given by the two methods. So for all studied grids, we obtain lower error for Kriging methods, as can be seen in table 1 and also in figure here. And we also studied the execution times and also speed up for the two parallelized algorithms. And it can be seen that IDW is much faster algorithm than Kriging algorithm due to complex calculus of Kriging. Also, the same results are exposed here, so it is obvious the execution times of Kriging is much higher than the execution time of IDW. And also after parallelization, the execution time is still much higher for Kriging algorithm. To conclude, both IDW and Kriging interpolation methods could be used for obtaining high-resolution geomagnetic maps. Both algorithms can be accelerated by CUDA programming, the speed up for IDW being up to 10 times higher than the speed up for Kriging algorithm. But by employing memory management technique and the performance of CUDA implementation, this could be improved, and better speed up could be achieved. Geomagnetic maps are obtained in a shorted execution time but the accuracy of the obtained data is lower when using IDW method than the one obtained using Kriging method. The use of CUDA for IDW and Kriging interpolation has been used to improve the computational efficiency and the accuracy of this technique. The potential of CUDA-based parallel algorithm and frameworks for improving the scalability and performance of IDW and Kriging interpolation on large-scale datasets is proven. And these results are expected to have a practical implication for many other fields that rely on interpolation techniques such as geology, meteorology, or environmental science. And thank you for your attention. Sorry for longer time.
Oh, no problem. Thank you for your presentation and your work. Any question? No? No question? Thank you again.
Thank you also. Have a nice day.
Thank you. So the last presentation is a compact RBFFD scheme for valuing financial derivatives based on short rate models. The author is Navda Thakur.
Yes, sir. I am
Hello.
here. Can you hear me?
Yeah.
Yeah. Good
Share your
afternoon.
screen.
Yeah. Can you confirm if you can see my screen?
Yeah, but go in full screen, please.
Yeah. Okay.
Okay, perfect.
Okay, so I'll start. I am Nodha Thakur, a senior lecturer in the Department of Mathematics, University of Mauritius. The title of my presentation is Compact RBFFD Scheme for Valuing Financial Derivatives Based on Short Rate Models. Modeling the term structure of interest rate is of crucial importance nowadays, since during times of financial crisis, government tends to adopt monetary policies which usually result in changes in interest rate. Therefore, it is more realistic to assume that interest rate fluctuate even over a short period of time. Numerous models have been proposed in financial engineering to describe the stochastic dynamics of interest rate. Interest rate options are among the most liquid options that trade in derivative markets, and due to the enormous size of these markets, there is a need to develop fast and accurate numerical methods for pricing these financial derivatives. A distinguishing feature of short-weight models is the need for the models to exhibit mean reversion and the volatility being dependent on the interest rate. Various stochastic models for the evolution of interest rates have been proposed, but due to the complexities of mean reversion and non-constant volatility, one-factor models are still popular among practitioners, although sophisticated multi-factor models are now available. Following the introduction of the popular Vasicek and Cox-Ingersoll-Ross model, diffusion processes have been often used in finance to model the evolution of interest rates, and these models admit analytical solutions for bond prices and European-style derivatives. The CKLS model has a more general form for the stochastic differential equation with greater ability in capturing the dynamics of the interest rate. For such cases, analytical solutions are not available and therefore numerical approaches are necessary for computing approximations to bond and bond option prices. The price of a zero-coupon bond under the CKLS model satisfies the PDE1, and the price of a European bond option and American bond option satisfy PDE2 and 3 respectively. While there exist many numerical techniques such as the recombining binomial and trinomial tree method of Kostabil and Masabo for the CIR model, and an analytical approximating formula for pricing bonds by Choi Weerjanto under the general CKLS model, as time to maturity increases or when the initial interest rate increases, the latter method leads to mispricing and numerical methods are therefore necessary. In this work, we propose a compact radial basis function method for solving the CKLS PDE for pricing interest rate derivatives. Meshless methods have become increasingly popular over the past years. Truly meshless approaches, such as the radial basis function collocation methods, are often based on a set of nodes scattered on the whole spatial domain, and we aim to fit a polynomial surface, as you can see here, on those nodes, and these methods achieve spectral convergence. In general, the global RBF method considers the whole domain. Although this method is simple to implement, as the number of nodes increases, the obtained matrix becomes ill-conditioned and the computational cost also increases. Therefore, to overcome the problem of ill-conditioning, various localized meshless methods have been recommended in the literature. The main idea behind the local RBF method is the utilization of the local subclusters nodes, as you can see in the figure, called the local domains of influence, while the local RBF for the approximation with the local RBF for the approximation of fields. For instance, if the red node is our reference node, instead of using all the nodes in the domain, we can only use the local support nodes, that is, the nearest yellow nodes. The most important benefit of utilizing the local method would be that the overlapping influence domain leads to many small matrices for every center node rather than a large collocation matrix. As a result, sparse global derivative matrices would be achieved, therefore less computer storage and flops are required by this method. In principle, it is probable to use both random nodal arrangement and uniform nodal arrangement, also known as RBF-FD, finite difference based RBF, In the method implementation, owing to the approach meshless feature, as you can see in the figures. Accuracy-wise, the efficiency of the uniform nodal arrangement is better than random nodes. The local OBF approach considers a stencil II, which consists of only the closest center nodes to the reference node. These closest nodes are known as the support nodes, which we denote by NS. The local OBF interpolant is given by equation 4. To illustrate how the local OBFFD method works, we consider 5 points and 3 support nodes. If, let's say, x2 is the center, the 3 closest nodes to it, as you can see, are x1, x2 itself, and x3. Therefore, the stencil consists of 1, 2, and 3. Similarly, if we take x3 as the center, then the 3 closest nodes would be x2, x3 itself, and x4. Then we obtain our I3, which is 2, 3, 4. Similarly, others can be obtained. To obtain the numerical scheme, we truncate the spatial domain and using a uniform mesh spacing and rewriting the CKLS-PD in the form of equation 5, we approximate the derivative terms BRR using a 3-node OBFFD approximation as shown here. A high-order compact methodology is then applied by replacing higher-order derivatives in terms of lower-order derivatives to obtain fourth-order scheme. For the time discretization, we use an implicit Euler scheme, and the accuracy is further enhanced with an S-stage extrapolation process. We next move to the numerical results. So we first consider the pricing of a zero-coupon bond with a short time to maturity of 0.5 year. It is observed that fourth-order accuracy are obtained for bond prices computed by the compact RBF method, whether it is for the CIO or the CSEC model, while for the 3-point RBFFD method, we obtain second-order convergence as expected. Now, for this short maturity problem, we observe close agreement between the Chewy-Weir-Jantu analytical approximation, an error of 10 power negative 6, and with the exact solution. So this was a small maturity problem. We next move to a longer maturity problem bond of 5 years. It is observed that the Chewy-Weir-Jantu solution is less accurate now with an error of 10 power negative 2. Similar accuracy are observed for the box methods by SOA, while the RBF 3 points and the compact RBF methods are still very accurate with second and fourth order convergence results. This is illustrated graphically. So as you can see, for a small maturity problem of t is equal to 1, all the 2 approaches match the exact solution, whereas as maturity increases, let's say for t is equal to 10, the Chewy-Weir-Jantu approximation leads to mispricing. And if we take t is equal to 30, a longer maturity bond, you will see that there is a mispricing using the Chewy-Weir-Jantu analytical approximation, while the proposed method, the compact RBF method, still agrees with the exact solution. So next we have the pricing of European option and American bond options. Again, fourth order convergence results are observed for European bond options and American bond options. We also report on some different values of the parameter gamma. Finally, to conclude, a localized compact radial basis function method was proposed for pricing interest rate derivatives when exact solutions are not available, as in the case of European and American options on bonds. Localized radial basis function based on OBFFT approximations for the spatial derivatives were first derived, and these are then adapted to the high-order compact methodology. Numerical results show that the method is fast and highly accurate with fourth-order convergent results. And also, it does not suffer from mispricing problems, which is common for long maturity problems. Other future work, the methodology can be extended to the pricing of contingent claims under two-factor interest rate models. So that's all. I thank you for your attention. If you have any questions, I would be pleased to answer.
Thank you. Thank you for your presentation.
Thank you, sir.
Any questions for? No? No questions? Thank you again. I don't see other authors, and for me, we can end the session. So, thank you all for participating. Thank you all, and goodbye.
Goodbye.
Bye.
Longer time.
No problem. Thank you for your presentation and your work.